Imagine staring at a 50-year-old biological mystery. Like a puzzle so incredibly complex, so fundamentally baffling, that literally thousands of brilliant scientists have spent their entire careers just, trying to solve it.
Yeah, exactly.
And then, imagine a computer just solving that exact mystery over a single weekend.
It's almost hard to wrap your head around.
Right. So today, for you, the learner diving in with us, we are tossing out the usual conversations about generative text or, making AI art.
Right.
We are looking at something far more profound. We are looking at how machine learning and these advanced neural networks are fundamentally breaking the speed limit of human discovery.
Yeah.
Basically acting as the ultimate scientific research assistant.
It really is a profound shift in how we do science.
Mm-hmm.
I mean, we're moving away from algorithms that just, retrieve information for us.
Like a glorified search engine.
Exactly. And we're moving to systems that are processing these world-altering calculations right in the background.
Wow.
We're talking about mapping biological structures, simulating astrophysics, and fundamentally changing the actual physical infrastructure of our world.
And the core mission for this deep dive is to unpack the mechanics of how this is actually happening. Like, we're examining how these systems process chaotic data at scales that completely defy human cognition.
Yeah, scales we can't even picture.
Right. And we are going to trace this from the microscopic level of human genetics all the way out to the simulation of distant galaxies.
But, I think it is important to set the philosophical foundation here before we look at the specific mechanisms.
Yeah, absolutely.
Because there is this underlying anxiety in the scientific community that massive computational power will somehow render the human scientist obsolete.
Oh, for sure. Like, we're going to be replaced by machines.
Exactly.
Yeah.
But research we are analyzing today points to a very different reality.
Okay.
This technology is not the end of human curiosity. It is an instrument.
An instrument, right.
Just like the electron microscope or the radio telescope didn't stop us from wondering about the universe.
They just let us see more of it.
Precisely. They allowed us to peer deeper into it. And these massive data processing models are doing the exact same thing for our conceptual understanding. They amplify our ability to explore the physical world.
So it's like a cognitive lens, not a replacement for human inquiry.
Yes, beautifully put.
Okay, let's unpack this by starting incredibly small and kind of, working our way outward.
Sounds good.
Let's begin at the microscopic level, deep inside human biology, specifically looking at modern medicine and healthcare.
Right, the oncology applications.
Yeah, exactly. The sources highlight some massive leaps in early disease detection, particularly in oncology, where computer vision models are detecting anomalies on scans far earlier than the human eye ever could.
And the mechanism behind that is really what makes it so revolutionary. Because a human radiologist, even one with 30 years of clinical experience, is fundamentally limited by the biological constraints of human vision.
Right, they can only see what they can see.
Exactly. They are looking for minute pixel-level anomalies on a high-resolution scan. But a deep learning model does not see the image the way human biology does.
Wait, really? How does it see it then?
It processes the scan as a vast matrix of numerical values. It cross-references the geometrical patterns of that specific scan against tens of millions of other scans in its training data simultaneously.
Oh, wow.
Yeah, so it is detecting mathematical deviations in the tissue structure that haven't even manifested as a visual mass yet.
That is wild. It makes me think of listening to a massive symphony orchestra.
Okay, I like that.
Right, like a highly trained human ear can listen to the performance and hear that the overall song sounds just a fraction of a beat off or a little out of tune.
Right.
But the diagnostic model, it's like an AI that's able to instantly isolate the sound of the third violinist in the back row playing a quarter tone flat.
That is a perfect analogy.
It filters through all the noise to find the exact microscopic deviation, like a super-powered diagnostic detector.
Mm-hmm.
And it is not just flagging the diseases, right? It is actively accelerating drug discovery.
Yes. And this is where we get into structural biology, which ties back to the 50-year mystery you mentioned at the start.
The protein folding.
Exactly. Protein folding. For decades, figuring out the three-dimensional shapes a protein would fold into based on its amino acid sequence took months, or sometimes even years, of really painstaking laboratory work.
Years for just one protein.
Yes. And now, these predictive models can determine those 3D structures in minutes.
That's just unbelievable.
And what's fascinating here is that when you know the exact shape of a disease-causing protein, you can design a highly specific chemical compound.
Meaning a drug.
Right, a drug that fits perfectly into its molecular pockets to neutralize it. It totally bypasses years of chemical trial and error.
And when you layer that molecular precision over, say, the sequencing of individual human DNA, you unlock what the sources point to as the holy grail of modern healthcare.
Personalized medicine.
Exactly. Personalized medicine. We are talking about moving away from prescribing a drug just because it worked for, 60% of the people in a clinical trial.
Yeah.
And instead, tailoring the molecular treatment to the patient's exact genetic architecture.
Because that shifts the entire paradigm of patient care. It moves it from a game of statistical averages to a framework of deterministic mapping.
Right.
The model looks at your specific genomic sequence, it identifies the pathogenic variants unique to your biology, and it determines the precise binding affinity a compound will have in your body.
Which is just staggering when you think about treating complex genetic disorders.
Oh, absolutely. It replaces the agonizing trial and error process with targeted precision.
But, the math required to untangle a three-dimensional protein structure or a human genome, it isn't fundamentally different from the math required to map massive chaotic systems outside our bodies.
Not at all.
Like, if these neural networks are this good at modeling the microecosystem of a cell, it makes total sense that the next frontier is applying them to the macroecosystem of the entire planet.
Exactly. The environmental applications operate on a completely different scale of variables, obviously.
Right.
But they rely on the exact same pattern recognition architecture.
So, digging into the source material, it groups this into three main planetary applications.
Let's hear them.
First is weather prediction. Traditional meteorology relies heavily on these huge physics engines that divide the atmosphere into a grid, and they calculate fluid dynamics, which literally takes supercomputers hours to run.
It's very computationally heavy.
Right. But the new models use deep learning to bypass those slow physics calculations, predicting extreme weather events with much higher accuracy and just a fraction of the computing cost.
It's incredible.
Then you have wildlife conservation using edge computing.
Yeah, the camera traps.
Exactly, running computer vision directly on remote camera traps to track endangered species in real time. It actually alerts authorities the exact second a poacher enters a protected zone.
Which is a huge leap for conservation.
And finally, sustainable agriculture, utilizing hyperlocal predictive modeling to optimize crop yields and reduce waste.
And the reason AI is so good at this is because agriculture, weather systems, and wildlife migration are deeply interconnected nonlinear systems.
Oh, right, they're constantly changing.
Exactly. They are driven by massive influxes of dynamic data. You have soil moisture levels, ocean temperature fluctuations, atmospheric pressure drops.
It's too much for a normal computer.
Right. Traditional linear algorithms just cannot process it. But these AI models thrive in chaotic data environments. They find the hidden correlations that we would just completely miss.
But wait, this actually brings us to a highly contested area in the source material, the climate data debate.
Ah, yes.
And we really need to be very objective here for the learner listening. Climate change remains one of the most intensely debated topics in the public sphere.
It really is.
You have highly credentialed voices on both the political left and the right looking at the same exact planet. But they often prioritize entirely different data sets. They highlight the statistics that support their specific geopolitical or economic arguments, and they kind of just discard the rest.
That happens quite a bit, yes.
So I have to challenge the premise here. Isn't an algorithm fundamentally biased by the humans who feed it?
That is a very fair question.
Right. If scientists are already disagreeing on which data matters, how does throwing a massive neural network at the problem actually resolve the human disagreement?
It is a critical pushback. And you are entirely right that an algorithm cannot magically resolve human ideological conflict.
Okay.
However, the advantage of a massive data processing model is its sheer capacity for aggregation.
Meaning it just takes in everything.
Exactly. Human researchers, due to their own cognitive limits, are forced to sample data. They select a subset of historical temperature records or a specific region of ice melt.
Because they can't read it all.
Right. But a sufficiently advanced model doesn't need to sample. It can ingest the entire global data set, every available satellite image, every historical temperature log, every ocean buoy reading, simultaneously.
Oh.
So it produces a synthesis based on the full mathematical geometry of the data without a pre-programmed political agenda to prove a specific point.
So it basically synthesizes the whole board rather than just zooming in on the convenient squares.
Precisely. But here's the crucial caveat that the source material makes explicitly clear.
What's that?
Aggregating the data does not guarantee flawless accuracy, and it certainly does not dictate policy.
Right.
The model provides a comprehensive, mathematically grounded map of the environment. It strips away the rhetorical spin of the data selection process.
Okay, so it gives you the raw picture.
Yes. But interpreting that map, deciding how to balance economic stability with environmental risk, and ultimately making the actual policy decision, that remains entirely on the shoulders of the human.
Ah, so the model synthesizes, but the human decides. Which is a really vital distinction. It gives us the data, but we still have to figure out how to actually navigate the physical world.
Right.
And navigating the physical world requires more than just data processing. It requires actuators. It requires muscle.
Which brings us to the physical realm.
Exactly. Out of the data centers and into engineering and robotics.
This is really the intersection where digital computation takes a physical shape.
So the sources focus heavily on heavy industry and logistics. We are seeing the deployment of smart factories where collaborative robots or cobots are utilizing computer vision for real-time quality assurance. They adapt to changes on the assembly line without needing to be manually reprogrammed.
Which saves massive amounts of time.
Absolutely. And then we are looking at autonomous vehicles using sensor fusion, combining LiDAR, radar, and optical cameras to navigate chaotic urban environments.
Practicing edge case scenarios at millisecond speeds.
Yeah, exactly. But the application that really stands out to me is disaster response.
Oh, yes.
Using reinforcement learning to train robots to navigate the chaotic, unpredictable geometry of a collapsed building, or a flood zone to locate survivors.
It really represents a fundamental evolution in how we deploy resources in a crisis.
But looking at this transition, you know, automating our supply chains, putting algorithms behind the wheel of our cars, sending machines into earthquake rubble.
Yeah.
I have to ask, so what does this all mean? Is the end game here purely economic? Is this really just about squeezing out more efficiency, cutting labor costs, and making supply chains run faster?
Well, if you look strictly at the financial reports, efficiency is certainly the driving incentive for the deployment.
Right. Companies want to save money.
Sure. But scientifically and practically, the implication goes far beyond economics.
How so?
When you examine disaster response robotics or autonomous transportation, you are actually looking at the mechanics of risk transfer.
Risk transfer?
Yes, you are taking the physical risk away from human tissue and transferring it to silicon and steel.
Oh, I see.
Because sending a human rescue team into a structurally compromised toxic environment is a massive liability to human life.
Obviously, yeah.
But a robot, utilizing simultaneous localization and mapping, which is called SLAM technology, can navigate that dark, toxic environment.
Right.
It dynamically maps the hazards without risking another human casualty.
That makes total sense.
And in the context of autonomous vehicles, the core objective isn't just a frictionless commute. It is the elimination of the human reaction time delay that results in fatal accidents.
So it's about safety.
It is utilizing computation to build physical resilience.
It is basically putting the machine in the line of fire. It acts as a physical buffer between fragile human biology and a chaotic world.
Exactly.
Okay, so we have scaled from the microarchitecture of human DNA to the macro systems of the Earth's climate out into the physical infrastructure of our cities.
We've covered a lot of ground.
We have, and the only logical frontier left in this deep dive is pushing past our atmosphere.
Deep space.
Yes. We are talking about fundamental physics, chemistry, and deep space exploration.
This is where computational power transcends the limitations of human sensory experience entirely.
The sources outline how these models are essentially accelerating fundamental science by exploring spaces we can't physically reach.
Right.
Like in chemistry and materials science, models are searching through the latent space of molecular combinations that have never even existed in nature.
To discover novel catalysts and next-generation battery materials.
Exactly. And in physics, rather than relying on brute force mathematical calculation, researchers are using neural networks as surrogate models to simulate the fluid dynamics of plasma.
Or to approximate the physics of black holes and dark matter.
Yeah, it's wild. And then you have space exploration, using satellite telemetry to autonomously map the topography of Mars.
Sifting through massive arrays of cosmic data to detect anomalous radio signals.
Right. But here's where it gets really interesting. The most conceptually fascinating application here is the deployment of autonomous spacecraft.
Deep space probes.
Deep space probes that navigate and execute mission parameters without a human in the loop.
None at all.
Think about the reality of that scenario. An autonomous spacecraft is essentially a solitary explorer.
It is entirely isolated by the laws of physics.
Exactly. The speed of light is a hard limit. If a probe is orbiting a moon of Jupiter and some unforeseen obstacle appears, a human controller back on Earth cannot pull a joystick to correct its course.
Because the telemetry takes over 40 minutes just to make a round trip.
Right. The craft has to utilize its own onboard logic to make a split-second survival decision, completely severed from human oversight.
And if we connect this to the bigger picture, we see the true utility of the technology.
Which is?
It allows us to reach into environments that are entirely hostile to our biology and physically out of reach of our communications.
Yeah.
We cannot stand near the event horizon of a black hole. We cannot manually hold the fundamental particles of quantum mechanics to see how they behave.
Right, obviously not.
We cannot remotely pilot a rover on the far side of Mars in real time. We are using these models to bridge the gap between human curiosity and the physical limitations of our bodies.
So the machine is reaching into the dark and running the physics for us.
Precisely.
It is a thrilling concept, but, hearing about a machine running the physics of the universe or autonomously piloting a spacecraft millions of miles away naturally triggers a fundamental concern.
The question of control.
Exactly. It begs the question of control, which leads us to the final section of the source material we need to cover today, the ethical architecture and the road ahead.
You really cannot deploy computational power at this scale without addressing the data structures that govern it.
Right.
The sources are very clear that blind trust in these models is scientifically dangerous.
Yeah, and the primary vulnerability highlighted across the research is the geometry of the training data itself, particularly regarding bias in medical modeling. We talked earlier about the model acting as a microscopic diagnostic detective, but if the foundational data that model was trained on is skewed,
which happens a lot.
Yeah, like say the genomic data matrix overwhelmingly represents only one specific demographic. The mathematical clusters it forms will be fundamentally flawed.
Yes.
It could provide wildly inaccurate diagnostic predictions for anyone outside that specific genetic group.
And furthermore, there is the massive dilemma of data privacy.
Oh, absolutely.
Because to build a highly accurate model for personalized medicine, you have to feed it millions of highly sensitive, completely unalterable human DNA sequences.
Right. Your DNA is your identity.
Exactly. The question of who owns that data and who secures the servers holding the actual blueprint to your biology is a massive unresolved issue.
And these are not just software bugs to be patched, are they?
No. These are structural flaws in how we gather and value human data. If the input matrix is biased, the output prediction is biased. It is a mathematical certainty.
And the stakes are only going to escalate from here.
Oh, for sure.
Looking at the future trajectories outlined in the sources, researchers are attempting to use these models to optimize the magnetic fields that control plasma inside a tokamak.
Potentially unlocking nuclear fusion.
Right. Solving the global energy crisis, they are projecting the discovery of synthetic elements and the deployment of AI-driven telescope arrays that dynamically adjust their own lenses to capture fleeting cosmic events.
It's a lot to dig in.
It really is. I have to admit, looking at the sheer velocity of this, if the model is mapping the genome, discovering the drugs, simulating the black hole, and steering the spacecraft, I'm just struggling to see where the human scientist actually fits into this workflow a decade from now. What exactly is left for us to do?
Well, this raises an important question. It is really the existential question at the heart of all this research.
Okay.
But the answer requires us to define what the machine actually is.
What do you mean?
A massive data processing model, no matter how sophisticated its neural network is fundamentally a hypothesis tester.
Not a hypothesis generator.
Exactly. It lacks inherent curiosity. The model can approximate the physics of a black hole, but it has no internal desire to understand why the universe is expanding.
Right. It doesn't care.
Right. It can map the precise chemical structure of a life-saving drug, but it has no concept of the societal ethics regarding how that drug should be priced, distributed, or regulated.
Oh, that makes sense.
The sheer speed of the computation does not negate the necessity of human judgment. It actually demands a much higher caliber of human oversight.
Because it's moving so fast.
Yes. The machine requires human curiosity to give it a target, and requires human ethics to manage the fallout of its discoveries.
So it is an incredibly powerful engine, but it is utterly useless without a navigator setting the destination.
Precisely. It is a symbiotic relationship between computational power and human intent.
Well, we have covered an immense amount of scientific ground today.
We really have.
We started at the cellular level, exploring how computer vision and structural biology are untangling the complex 3D architecture of proteins.
And mapping individual DNA sequences to usher in personalized medicine.
Right. We zoomed out to the planetary scale, looking at how neural networks bypass traditional physics engines to predict volatile weather, utilize edge computing for wildlife conservation, and aggregate massive, chaotic climate data sets without political spin.
And then we examined how that data takes physical form, transferring risk from human biology to robotics in disaster response and autonomous navigation.
And finally, we pushed past the atmosphere, exploring how surrogate models are simulating the physics of the cosmos, discovering novel chemical compounds, and acting as solitary explorers in deep space.
It's an incredible journey.
It is. And through every layer of this deep dive, the central theme remains constant. This technology is not replacing human ingenuity.
No, it's not.
It is an instrument built to amplify our understanding of the universe, but its value is entirely dependent on the structural integrity of the data we feed it and the ethical rigor we apply to its outputs.
And as we look toward the horizon of these breakthroughs, considering everything we've synthesized today, I want to leave you, the learner, with a final thought to examine.
Oh, I like that.
If these models eventually absorb all the heavy lifting, if they execute the mathematical simulations, process the vast genomic data sets, and run all the repetitive laboratory permutations across every single scientific discipline,
Right.
will the future scientist need to be a technical mathematical expert at all? Or will the scientist of tomorrow simply be a deeply curious philosopher whose primary and most vital skill is just knowing how to ask the machine the right questions?
Wow. That is an incredible paradigm shift to think about. Thank you for joining us on this deep dive into the mechanics of discovery. Keep exploring the variables, keep questioning the world around you, and we will catch you next time.